Hi, thank you. So I don't have too much to say. I'm the organizer of the seminar series, and as our first distinguished speaker, we will have Seung-Ju Hwang, who's a rising star in the area of deep learning. And you might have noticed that this announcement of this talk was very late, just a few days ago, and there's actually a very good reason for that. Instead of just talking about an old topic, Professor Seung-Ju Hwang decided to talk about his latest and greatest cutting-edge research, and so I think this talk will be a very good treat for all of us. So, Professor Hwang, take it away.
Thank you for the nice introduction, and I'm really honored to be the first speaker in this seminar series. Okay, so actually I gave this talk a couple of times at KAIST, so I changed the title a little bit so that you might not know that I'm talking about the same thing over and over again. So the title was originally large-scale deep learning, but I changed it to massive deep learning. So this is more like our goal, okay, our long-term goal. Okay, so my research interest here is on solving real-world problems with principled machine learning approaches. So here the difference is that I do not only want to apply existing machine learning approaches to like the real problems, but so it's more like that we get insights and we just explore new challenges from the real problems and then try to solve this new problem using machine learning. Okay? And there exists a lot of challenges in applying artificial intelligence or machine learning to real world, and that is why we started this research center. So we work on Mars AI. So Mars stands for Massive, Automated, and Reliable and Secure AI. Okay. And so to solve real world problems, our artificial intelligence system should be able to scale to handle massive amount of data, tasks, parameters, and users, and it should be also automated so that it could be used by just a non-expert in machine learning, so that the AI handles everything automatically, like from model selection, training, inference, and modification, and adaptation to new tasks. And our model should be also reliable. So if we want to apply our model to like autonomous driving or like medical diagnosis, for those problems the AI should not fail, right? So the model should be very safe and it should work predictable, and there should be reliability in an entire process of training and using this artificial intelligence from data collection to prediction. And there could be adversarial attacks. So, I mean, I don't know if you read the recent news, but there were people who attempted to just attack the autonomous driving vehicles, so Tesla vehicles that drives autonomously on the roads, and that was by applying some kind of like a small modification of the traffic signboard. Okay? So by just making making a small modification of the traffic signboard, we can make the AI to believe that the signboard is a yield sign instead of like a stop sign. So that kind of so we have to defend against those adversarial attacks, and also need to prevent the leakage of the data and parameters. And so all of these are very important problems, and I actually work on all of these topics, okay, including so I work on like the Bayesian optimization and model architecture search that's related to automated AI, and also on like Bayesian models that are more related to reliable AI, and also adversarial learnings. But so I wanted to prepare something new this time, but didn't have time, and I really wanted to introduce you the massive AI that we are working on. So I'm actually leading, not really leading, but I'm a part of this massive AI part in the Mars AI Center, and So we are a group of AI and systems faculty members, the researchers that work on realizing this massive AI system. Okay. So as a motivation, okay. So this is becoming like daily. So I'm using this too much. So our goal is to. So my original goal was to build a visual recognition system that can recognize almost all named objects in the world, like including all the products. Okay. So the system that I envisioned was something like this. So we put some like the wearable cameras that automatically detect everything on the road and test the user, just provide some user some useful information. Okay. If the recognition system can only recognize objects at this level, at the basic object category level, such as bus, bicycle, and car, I mean, it could be cool. It could look cool, but it's not going to give you any useful information, right? So to be able to provide the users useful information, the model should be able to recognize hundreds and millions of object categories, including all the products. You should recognize the bicycles by their product names instead of the category bicycle to send the users to the purchase page. And we need to recognize the correct line number for these buses to provide some useful information, like the route. Okay? So deep learning models have achieved like the human level performances for the classification of like 1,000 visual categories. So this is actually an impressive achievement. So if we consider top 5 prediction, where the model makes 5 predictions and where we evaluate whether the correct answer is within those 5 predictions, then the machine does better than the human. So the best deep learning model surpasses the human performance by 2%. But if you just increase the number of the classes, the accuracy goes down to 42%. In this case, a system with 42% accuracy is not practical, right? So we cannot really use this model for real-world applications, right? So there are a lot of challenges. So not just about the accuracy, but there will be also some challenges regarding the efficiency and scalability. So to scale deep learning models to classifications of like millions of object categories, we'll need to solve new challenges that come with a large number of classes, that cause a large number of classes and large number of parameters, and large number of large data size. Okay, so there will be a large number of classes or tasks. Okay, so here I'm assuming that we are solving a classification problem, but this could be actually individual tasks that are solving different problems. If we consider like a disease diagnosis problem, then each of these tasks might correspond to the diagnosis of some disease, right? And we can have like millions of different diseases. And the network size will become larger and larger if we need to like classify or predict like tens of millions of tasks or classes. And also the data set size becomes an issue. Okay, so how to handle this efficiently will be an issue. Okay. So my research is mostly focused on tackling large number of classes and large number of parameters. Okay, because the handling large number of data is more like a systems issue. Okay, so my research objective is to develop scalable models and algorithms that can achieve both high accuracy and efficiency on large-scale problems. Okay, so not only the accuracy is the problem, but obtaining efficiency with this large number of clashes and parameters is also a very important problem. And so these are my collaborators, mostly my lab members and Professor Yang and Professor Connie Kim from Seoul National University and many others. Okay, so let's go to the first challenge on tackling large number of clashes. Okay, so if we have large number of clashes, that brings in many new challenges. And the first challenge is fine-grained categorization problem. As a categorization problem or the classification problem grows in scale, the space of the classes become more and more dense. So that means that we'll have more confusion between similar object categories. So in some cases, the intra-class distances might be actually larger than the inter-class different distances. Okay? So this Tesla Model S is a sedan, but it could look more like a sports car. Okay, so that due to this problem, so most of the confusion, even when we try to classify like 20,000 categories, so most of the confusion happens at a very fine level. Okay, so if the ground truth is like this flower, then most of the mistakes in most of the incorrect predictions is classifying the given instance as one of these very similarly looking flowers. Okay? So even if the top 1 accuracy is very low, if we consider the top 10 or top 20 accuracy, prediction accuracy, then the accuracy is pretty high, like 70%. So that means that if we can make correct prediction when we classify between these fine-grained clashes, then we can achieve a large improvement in accuracy. Okay, so one of the solutions to this problem is to make the deep neural network to focus on fine-grained classification task. Okay. So in order to do this, we propose a new classifier that replaces the original software classifier that stochastically drops clashes from the classifier with some input-dependent probability. So based on what input is given, we want to focus on the classification problem that is actually relevant to this input. So if we have an input image where this cat is wearing a lion mane, then we want to focus on the target. We want to focus on the clashes cat and lion, because this is confused most with lions. So there's a very low chance that this will be confused with whale, right? So we assign high probability of solving the classification problem between lion and cat. So the target classes should be retained, and non-target classes should be retained with some probability, and this probability is long. Okay. So, and this class sampling is happening at every iteration. So at every iteration we are solving a different problem. But in that, we solve problems that are more relevant to the input. So that we solve problems with that classify between lion and cat more than the problem that classify between cat and whale. Okay? So if we have an input that looks like this, so we have a spotty category input, then we focus on the problem of classifying between cat and jaguar. Okay? So the retained probability for jaguar goes high, okay? While we have low probability for lion. Okay? So this could be understood as an ensemble of classifiers, because we have many different classifiers that are averaged together at the end. So it's like a dropout for a software classifier. So for softmax classifiers, each of the outputs will output the probability of having of the instance being classified as one of the target clashes. And the dropmax classifier has the same output, but we have another binary variable, binary mask variable that's learned to drop some of the clashes. Okay? And we want to learn this probability. Okay, so we learn this using variational base, and the results show that this stochastic classifier obtains much lower error compared to the base softmax classifier, and we achieve quite a high, quite large improvement on fine-grained data sets. So AWA and CUB are fine-grained data sets. So this one contains clashes of the different animal clashes, and this contains different bird species. And we can also see that our regularizer reduces the chance of overfitting. So the gap between the training loss and the test loss is significantly reduced using our method. And if you examine some of these dropout probabilities that are learned using our classifier, and for easy examples, it's just working as a second classifier. Okay. But for difficult examples, such as one here, so this instance could be classified either at 3 or 5, then our classifier sets high probability for these confusion clashes and low and almost zero probability for all the others. So it's focusing on this fine-grained classification problem. So it doesn't really focus on problems that the classifier will not make any mistakes, and it's focusing on problems that is difficult. Okay? And these are the clashes that have high retain probability, and these are the target clashes, and you can see that the clashes that are retained are the ones that are most confused with the target class. Okay, so another challenge in large-scale problem is that, and for real-world problems, is that real-world data sets are largely imbalanced. In terms of both the number of training instances, so for common clashes such as person and car, we might have like millions of instances. But for very rare object clashes such as panda ant, we might only have like very few training instances because they are rare in our visual world. And also tests have different difficulties. So classifying zebra as zebra could be very easy because due to their distinctive stripes pattern. But recognizing plastic bag is a much more difficult problem due to large variances in their colors and textures. Okay, to solve this problem, we can use multi-task learning. So this is a very popular solution when we work with few training instances. And so the main idea here is that we try to share some knowledge between the classes, such that we share knowledge between like very similar classes such as zebra and donkey or donkey. Okay? But the problem is that when using multitask learning, there's negative transfer. In which case, the unreliable models that's trained on difficult problems like zebra tail lizard negatively affects the good models. So when we obtain improvements on the prediction of zebra tail lizard, at the same time, we lose accuracy on a very easy task, like predicting zebra. And this is due to the symmetric nature of knowledge transfer. So people have criticized multitask learning for not making like improvements, but this was due to some of the accuracy drops in the easier problems, in the reliable models that solve for easier problems. So to prevent such negative transfer, we have developed an asymmetric multitask learning model that allows the task with low task growth and large number of training instances to transfer more to tasks with small number of clashes or the tasks that are difficult to solve, so that they have high loss. Yeah, so I'm not going to go into details of how we implemented this model, but we allow this kind of asymmetric knowledge transfer between tasks. In an inter-task transfer, when we learn this inter-task transfer matrix. So it effectively prevents overfitting. So we compare our model against existing symmetric multitask learning models, and you can see that for symmetric multitask learning model that are plotted in blue, for some tests it makes large improvements, but for some tests it degenerates the performance over the single task learning model. So this is an improvement over the single task learning model. But our model makes improvement on almost all tasks, without any performance degeneration on any of the tasks. And this is actually very important for fairness as well. Because if you think of each of the tasks as the diagnosis of certain disease, just improving on the diagnosis of one disease while degenerating the performance on the other is not really the result that we want, right, in terms of fairness. And our model makes large improvements on multiple data sets. And there is certain limitations of this inter-task transfer model, because we have to combine some task parameters to generate the task parameter for the target class, but it doesn't always happen, right? So combining tiger and horse will not give us the zebra, right? It will become something just in between. So what we want to transfer is actually the stripe pattern in the tiger and this body shape of the horse, right? So instead of doing task-to-task transfer, we can do task-to-feature transfer. So we use an autoencoder where we reconstruct the features from the task parameters. But here we allow for asymmetric transfer such that reliable models can contribute more to the reconstruction of the features, while unreliable predictors are not used. Okay? So by doing this, we can prevent negative transfer. So by doing this, we can also learn less noisy features compared to the symmetric multitask learning models that are more close to the true basis. And also, this model is more scalable because it doesn't do inter-task transfer. So to be able to do inter-task transfer, we'll need a transfer matrix that grows quadratically. But for the case of task to feature transfer, since the dimensionality of the features could be very low, we can make actually sublinear increase. We can make about linear increase in the size of the model. Okay, so another solution to this imbalance problem, or working with few shot learning problems, is to use meta learning. So the meta-learning is the method that trains the model to generalize over a distribution of tasks, where we randomly sample the task from a task distribution. So at each time we randomly sample some of the classes from the set of the classes, and then try to classify between these sample classes. And then such that this model is not trained on a specific task, but is trained over a distribution of this classification task. And this is a very popular approach for few-shot classification, because the meta-knowledge that's obtained over the distribution of tasks could be utilized when we classify between unseen classes, or when we classify between classes with few training instances. But the problem is that these meta-learning approaches in the past are only targeting few-shot classification problem. So, but they cannot be applied to real-world problems where we have imbalanced data sets. So, for classes with few instances, we might want to use this meta-learner. But for classes with large number of instances, we might just want to train a model that's specific for this task. So instead of just using instead of just training a meta-learning that is trained to do well on all the tasks, we learn to balance between this meta-learner and the task adaptive learner. Okay? So we decide how much to take from this meta-learner and how much to optimize for the given task. Okay, so for tasks with all the classes with few instances or out of distribution, then we make them to stay closer to the meta parameter. But for tasks that have large number of instances, so that they do not really need the meta-learning and meta-knowledge, we allow them to deviate much from this meta model. And we obtain this balancing parameter as a function of the task distribution. And we encode this task distribution as a set of class distributions. Okay, so in each task we have classes, and the classes will have certain degree of imbalance. And we capture that by capturing the moment of this distribution, such as mean, variance, and skewness and kurtosis. Okay? So we want to represent this imbalance even in the representation space where we encode the set. And based on this set encoding, we learn the two balancing parameters that decide how much to use from the meta-learner and how much to deviate from the meta-learner. And the results show that our model significantly outperforms the state-of-the-art meta-learning models for imbalanced data sets. And our model is also able to handle out-of-distribution tasks as well. So when we train our model on one data set and test on the other, then we can make much larger improvements over the baselines. And you can see that the learned balancing parameter, the amount of the balancing parameter is actually reasonable, so that for in-distribution task, for out-of-distribution task, and when we work with few training instances, the model tries to make the learned model to stay closer to the original meta parameter. But if if the task is in distribution, and if we have large number of training examples for the task, then it can deviate much from the meta parameter. And the second problem, the second challenge that we need to solve is the problem with large number of parameters. Okay. If we have really large number of classes, I mean, for the softmax, even for just storing the gradient and weight for the softmax classifier, we might need about 131 gigabytes. That's too large to fit into the video memory of any commercial GPUs. Okay, so we need to make the size of the model to be manageable. And at the same time, we should also deal with the training and evaluation time, so the computation overhead as well. Because if we have large number of parameters, then it might take a lot of time to compute them as well. So the first solution to this problem is utilizing sparsity, so that we make the model to have mostly 0 parameters. But the problem is that with the sparsity, utilizing sparsity, is that sparse models often obtain lower accuracy when we increase the sparsity. So as we make our model to be more efficient, it loses accuracy. So there's a trade-off between accuracy and efficiency. So in one of our early work, we proposed a combined group and exclusive sparsity, which basically lets the model to select the most useful features from the lower layer, and while at the same time make the representations learn that the upper layer to be different from each other. Okay, so the group sparsity, the sharing, and it drops the features that are not used often by the upper level neurons, and the exclusive sparsity tries to make the representation at upper layer to be as different as possible to reduce redundancy. Okay, so there's some sharing and competition going on, and we balance them differently at different layers of the neural network. And when we couple this model with iterative pruning, where we alternate between the training of the model and pruning. So the original model is trained with L2 regularization. In that case, when you use only the 10% of the parameters, then you're going to have some accuracy degeneration. Okay? But when using our model, it doesn't suffer from the accuracy degeneration, and sometimes the accuracy improves. And this is due to better utilization of the network capacity. And another way to sparsify the networks is to learn the binary dropout rates for each of the neurons, or the filters. Okay? So we usually set the dropout rate to be some constant number, like 0.5. But we can actually learn the dropout rate differently for each of the filters or each of the neurons. And when the dropout rate goes to 1, that means that we are not going to use that neuron anymore. Then we can sparsify the network. We can just drop the network or the filters, and we drop the neuron or the filter. And this is done by using some sampling from some sparsity inducing prior. I mean, learning the posterior for this dropout for each of the neurons or the filters, using some sparsity inducing prior, they have high density around 0. Okay? So in this case, in most of the cases, we will be sampling from 0. Okay? So we approximate this using some approximate posterior, so that we can have a colorful solution for our radiation inference. And to remove the redundancy among the features, we can further make the driver rate to be dependent on the input, such that for each of the inputs, the driver rate is set differently for each neuron or filter. Okay? So given a bicycle, we might try to retain the feature that describe the chain. For train, we might retain the feature that describe railroads, for instance, so that they retain different features based on the input. Okay? So we test our model, both our input independent model and input dependent model, and against state-of-the-art network sparsification methods. And these are the blue dotted line and the purple dotted line shows the results of our model, and they obtain much higher speed up in computation measured by flock, while achieving much lower error. So they obtain much lower error with higher speed up. Okay, so and another solution to handle large number of parameters is to use distributed deep learning, use parallelization. So we can distribute the model parameter to different machines or different processors. But the main problem that's incurred by that is that there will be a large communication overhead, large communication cost between the machines or between the processors. So in most cases, if you just naively apply parallelization, it's going to result in a much slower processing, slower inference. Okay, to handle this, we propose to semantically split up the network into a hierarchy of the disjoint subnetwork. So given a base network, we want to split up the network based on some class semantics automatically, so that we have a hierarchy of disjoint subnetwork. So that means that between the two subnetworks we have here, there will be no communication happening at all. So there will be no connections between these two. So we don't have to have any communication. Okay? So the only communication that might happen is at the final softmax layer, but this could be done in a very cheap way. And this can be achieved because some of the features are used by only some of the classes. Like this real-life feature will be used by classes such as trucks and bus, but they will not be used by classes such as man, woman, and boy. And the face feature will not be used by these vehicle classes. And vice versa, right? So based on this intuition, we can obtain block diagonal matrices such that we have some groups of classes that only work on certain features. Then, at each layer, our weight matrix will be block diagonal. Okay? And as they are block diagonal, these different blocks could be run on different processors or different GPUs. Okay? So now the problem has become more manageable. And we saw that the accuracy does not drop, even if we split the network. So by using only like 25% of the parameters, we could achieve almost similar performance to the full network. And at the same time, if we just use naive parallelization of the deep neural network models, they result in like lower speed, processing speed. But if we apply our model, it achieves almost linear speedups to the number of processors or number of GPUs. So there are some overheads, but this is more like an engineering issue. So by just eliminating the communication overhead, we could make the speed up to be really large compared to this model. And another thing that we are trying to work on, another topic that we are trying to work on is working with massive users, large number of users. And when we work with large number of users, then there's a problem of how to assign the resources to each user. And the amount of the resources that's available for each user might dynamically change. So if there are, if it's near a paper submission deadline, there could be a lot of users submitting a lot of jobs. Okay? Like during like Christmas holidays, we might have just one person like running all the jobs, right? So we have different availability of processors and memory, and we have different number of users. So I'm trying to develop models that can dynamically change its size. Okay, based on the resource availability. Okay. And another challenge in working in large number of parameters is the architecture and the hyperparameter search. So if we want to find the model, find the network architecture that works well for the given task. So one of the ways to achieve this is by the top-down search. Okay? We just exhaustively perform grid search over how many neurons and to use at each layer and how many layers we use for the entire network. Okay? But this is impractical. So instead of doing this, we want to search for the network structure in a bottom-up manner. Okay? So instead of just trying to build a network using all the classes or all the tasks, we incrementally introduce a new class and try to dynamically grow the network in size. But one of the problems that arise here is that if the classes that are trained earlier is very different from the classes that are learned later, then there will be some performance degeneration because it has to utilize the representation that are very much different and that are not very useful for describing the given task. And another problem is semantic drift. If the new class affects the representations that are already learned, so they might negatively affect the tasks that are learned earlier. Okay, so we solve this problem by proposing a deep network that can selectively utilize the prior knowledge. So, if we have a class zebra, then it's going to only affect the features that describe the features of zebra, like stripes. And then, if the current network cannot adequately represent the new class, then we want to dynamically add new hidden units or new filters while increasing the network size by the amount that's necessary. Okay, so this is done by selective retraining, where we identify the part that should be retrained and dynamically expanding the network with only the necessary number of neurons, and split the network when the network is drifted away too much from its original meaning. And the results show that our model, this dynamically expandable network model, achieves much higher accuracy with much lower number of parameters. Okay? So the accuracy, so this is a part of accuracy over capacity, and when compared to existing continual learning models, it works much better. And achieves much lower capacity. Okay? And when compared against models that were trained for all classes or all tasks at once, I mean, it still does better. So the black lines, the DNMTL is the full model that's trained with all the tasks and all the classes. And the reason that our model obtains better performance is because this DNMTL, also these neural network models are all manually designed. Okay? So that means the architecture that has been found by our bottom-up incremental learning was more optimal compared to the manually designed architectures. And some of the recent work that I'm trying to make the network expansion to be more manageable, because in many of the expansion-based continuous learning methods, sometimes increase the network size too much due to redundancy. So instead of just expanding the network by adding in new neurons, we just learned additive parameters. We learned parameters that are added to a shared parameter. But this additional parameter is extremely sparse, so it only modifies the parameters that should be modified to handle the new task. Okay? So the task parameter for all these tasks can be represented as a sum of the shared parameter plus the extremely sparse parameter for each task. So by using this model, we can obtain even larger accuracy improvement with much lower capacity compared to dynamically expandable networks. Okay, so these triangles are our new models, and this square is the dynamically expandable network. And this R shell is basically a version of them where it uses reinforcement learning to increase the network size. So the performance over capacity or performance over training time is much better when compared to existing network expansion-based methods. And also it can solve the task order dependency problem, where the network performance changes, model performance changes based on the order it's trained. Okay? Because when we do bottom-up training of the model, based on which order we train the model, the final accuracy might have large discrepancy. So for one sequence, we might have this kind of performance for each task, and for another sequence, we might have this kind of performance. But this is actually not very good for fairness. Okay? If we try to perform medical diagnosis, and this kind of discrepancy in accuracy is not desirable. But our model, since it decomposes the shared parameter with the task adaptive parameter, they mostly convert to a similar solution. So the discrepancy based on the task order sequence is very small. So this shows that the result that our model obtains the model that's order robust. So based on which order, regardless of which order is trained, it obtains similar performances, while the baseline models do not. And as a next step, we are trying to make this sharing to happen in a hierarchical manner. Okay, so we can have hierarchical set of shared parameters, so that even when we have large number of tasks, the number of parameters just logarithmically increases. Okay, the final topic that I'm going to the final problem that I'm going to mention is on fast train. So instead of using human design static update rules, for optimization of a deep neural network, we can use some learned update rule using a meta network. And by learning the update rule, we aim to make the model to converge faster to a solution that generalizes better. Okay? So there are two goals. So we want efficiency and we want better solution. So currently we are working on a model that selectively updates the network parameters to expedite the training process. So this is again a model to handle large number of parameters. So the original stochastic gradient descent is going to compute the gradient for every parameter, okay? Every parameter in the given model. But we want to first we want to focus on very sparse set of subnetwork, sparse set of neurons or sparse set of parameters, so that we update a subnetwork instead of the full network. So by using this selective update, we can expedite the training process greatly. And also, we have a conjecture that this sparse update may obtain smoother low surfaces. So having smoother low surfaces will result in better generalization. So this is another desirable property of an optimizer. And the results we have obtained so far shows that the proposed learned optimizer converges much faster in terms of the world clock time. So the existing models only reported the convergence over the number of iterations. But in fact, at each iteration, the computation cost was much larger. But in our case, the computation at each iteration is only a fraction of the original. Okay, so we can achieve speed up in world clock time. And another thing that we observe is that as we train the model on, the spatial level went up. So in the beginning, the update was not that sparse. So it was trying to compute the gradient from all the parameters, but as it trains on and as it converges more to the solution, it obtained much more sparse solution. It made much more sparse updates. And since each gradient update is much cheaper with our selective gradient update, we can now search for many different directions. So since our model is Bayesian and stochastic, we can sample different gradients and different directions to evaluate at multiple points, and we can go to a direction that minimizes the loss most. Okay, and as a long-term goal, we try to make this optimizer to generalize over many different data sets and many different architectures. So currently, the meta update rule is trained alongside the model. So it's for a single model and single data set, but we can make it to generate better. Okay? So in future work, we try to build a machine learning platform for this massive deep learning by incorporating and so by assembling all these components. So we want to build this parallel network and network structural learning, sparsification, enhance those, and the learnable optimizer in a single machine learning framework. And we also want to perform dynamic data and model parallelization in a resource adaptive manner for multiple users. Okay? But this is a future work. So we have now built each individual component. So this is more like our next step. And we can apply this massive deep learning to many different real-world problems, like product identification, So as you might all know, so this product identification is actually used in with Amazon Go or like the cashier systems in convenience stores. So this is actually my student who is graduating. And we can also apply this massive deep learning model for like medical diagnosis, because for medical diagnosis we might have like millions of different diseases with many rare diseases that only comes with few training instances. So our model that can handle data imbalance could be very useful in this case. And the models that we have built for massive deep learning is actually improving the efficiency of the deep neural networks. So they could be used for deep learning on resource-limited devices, such as on the embedded GPUs or neural processing units. So I'm working toward this direction as well. So for working in low-power computing devices, we also need to. So we don't only make the network to be smaller in terms of number of connections, but we can also quantize them. So that instead of using like the 32 bits to represent each weight, we can also use small number of bits, like 2 bits or like 3 bits. Okay? So this is also closely related to massive deep learning, while they are trying to solve a completely different problem. So massive deep learning tries to solve a large problem that cannot be handled with currently available learning systems. So this tries to handle a small problem on a resource-limited devices. Okay? So this is it. And do you have any questions? Okay.
I think your conjecture that the sparse gradient induces better generalization is interesting.
Yeah.
And so have you just kind of tried to validate this conjecture just by sparsifying the gradient of the regular optimizer versus stochastic gradient, so you can just try to sparsify the gradients?
Right. So actually, this is just a conjecture, but since my students haven't really done the experiment to validate the claim, we are still unsure. But we try. So there are some ways to approximate the Lipschitzness of the function. So we are trying to use that method to see if our sparse gradient update rule improves the Lipschitzness, so that it obtains a much flatter solution, like smoother solution. But this is not done yet. Okay.
Can I ask?
Yeah.
I'm very interested about the data imbalance for
Yes.
digital data. For example, for some application for medical image for cancer detection. So most of our training data are labeled as no cancer definitely, but only like 10% of data are labeled as cancer. We have cancer based on the medical image.
I see.
So for this,
there are
for this kind of case, definitely when you classify as cancer, is more important than classify as no cancer, right?
Right.
So based on your presentation, so what kind of method should we go for this kind of case?
So you are referring to the case where we have very small number of positive instances and large number of negative instances, right?
Yeah.
I don't know. So in most cases, we can just perform sampling. When we train the model, we can sample the number of the instances for the positive and the negative instances to be similar. Or another way is to just normalize the loss by the number of the positive and negative instances, so that each of the negative instances will have much smaller loss compared to positive instances. So those are just the common approaches to tackle the imbalance. But what I presented is more like imbalance in multi-class classification. So in your case, it's like a binary classification, right? So, no, any other question? Okay.
What are the requests for you of architectural support that you need to study massive neural network?
Okay, so architectural support. I think so. The most important part is some architecture that can minimize the communication cost between multiple processors. So, and when we do machine deep learning, so there are two things. So one is the communication cost, and the other is the memory latency. So if we analyze the model for bottleneck, then the most bottleneck happens at the memory access level rather than in computation. So we need ways to make the memory to be faster and reduce the communication cost between processors. Okay. If there's no other question, then we can just.
Thank you again.